Every modern engineering system you rely on, airplanes, power grids, smartphones, exists because engineers made deliberate compromises. These systems are not optimized for one single goal. They are optimized around trade-offs: speed versus safety, cost versus reliability, efficiency versus durability. Today, we'll break down why trade-offs are unavoidable in engineering and how they quietly shape the technology that runs the modern world. In engineering, the idea of a perfect system is a myth. Every design decision improves one aspect while constraining another. This is not a flaw in engineering. It is a fundamental reality of physics, materials, economics, and human use. Engineers describe this reality using trade-off spaces. Improving performance often increases cost. Improving efficiency may reduce robustness. Improving safety usually adds weight, complexity, or redundancy. These trade-offs exist because real-world systems are bound by constraints: limited materials, finite energy, manufacturing tolerances, human behavior, and budgets. Engineering is not about eliminating constraints. It is about choosing which constraints matter most. Organizations like NASA, SAE, and ISO explicitly require engineers to document trade-offs during system design. This ensures decisions are intentional, not accidental. In this video, we'll explore 3 core trade-off categories using real engineering examples. By the end, you'll understand why modern engineering systems look the way they do and why better almost always means better at the expense of something else. One of the most fundamental trade-offs in engineering is performance versus reliability. Pushing a system to operate faster, hotter, lighter, or more powerfully increases stress on materials and components. Higher stress accelerates fatigue, wear, and failure. Consider jet engines. Modern turbofan engines operate at temperatures hotter than the melting point of their metal components. They only survive because of advanced alloys, ceramic coatings, and internal cooling channels. These technologies enable high performance, but they also increase cost, maintenance complexity, and inspection requirements. Engineers must decide how close to the limit a system should operate. Operating closer to physical limits improves efficiency and output, but reduces safety margins. This trade-off is quantified using reliability engineering. Engineers calculate metrics like mean time between failures, or MTBF. As performance increases, MTBF often decreases unless additional safeguards are added. That's why high-performance systems often include redundancy, derating, or strict maintenance schedules. Commercial aircraft engines are deliberately over-designed for durability, even though lighter engines would improve fuel efficiency. The reliability requirement dominates the performance trade-off. NASA explicitly applies this principle in spacecraft design. Systems are often operated well below their theoretical limits to ensure predictable behavior over long missions. Automotive powertrains illustrate the same principle. An engine tuned for peak power typically requires increased airflow and higher cylinder pressures, which elevate internal temperatures and mechanical stress. These conditions accelerate wear on components such as pistons, bearings, valves, and turbochargers. Pursuing maximum output therefore places greater demands on materials, cooling capacity, and structural margins. Engineers must decide how much stress the system can tolerate over its intended service life. The vehicle ultimately reflects a negotiated balance between performance expectations and durability targets. In short, maximum performance is rarely the goal. Predictable, repeatable performance is. Another unavoidable trade-off is cost versus safety. Improving safety almost always increases cost. Safer materials, redundant components, extensive testing, and regulatory compliance all require resources. The challenge is that safety improvements follow a curve of diminishing returns. Reducing risk from high to moderate is often inexpensive. Reducing risk from very low to near zero becomes exponentially costly. Consider automotive engineering again. Adding airbags, crumple zones, and electronic stability control dramatically improved safety at reasonable cost. But designing a car to be absolutely crash-proof would make it prohibitively expensive, heavy, and impractical. Engineers therefore use risk analysis frameworks like failure mode and effects analysis, or FMEA. Each potential failure is scored based on severity, probability, and detectability. Safety investments are focused where they reduce the most risk per dollar. The same principle applies to infrastructure. Power grids are designed to tolerate failures without collapsing, but not to prevent every possible outage. Designing for absolute continuity would require massive overbuilding and redundancy far beyond economic feasibility. Regulatory bodies like the FAA and NHTSA define acceptable risk thresholds. Engineering systems are designed to meet or slightly exceed these thresholds, not eliminate risk entirely. This is not negligence, it is rational engineering under real-world constraints. Another common trade-off is efficiency versus robustness. Efficiency is often celebrated in modern engineering, but it comes with its own trade-offs, particularly against robustness. An efficient system uses minimal energy, material, or time to perform its function. A robust system tolerates variability, misuse, and unexpected conditions. Just-in-time manufacturing is a classic example. It minimizes inventory and maximizes efficiency, but it also reduces buffers. When disruptions occur, such as supply chain shocks, the system becomes fragile. The same applies to mechanical systems. Tight tolerances improve efficiency, but reduce tolerance to dirt, wear, or misalignment. Looser tolerances reduce efficiency, but increase durability. Engineers must decide how much inefficiency to intentionally include. Extra material, thermal margin, or control authority often acts as a buffer against uncertainty. NASA frequently favors robustness over efficiency. Spacecraft systems often include extra mass, redundant pathways, and conservative operating ranges. These choices reduce efficiency, but increase mission success probability. Efficient systems excel in ideal conditions. Robust systems survive real ones. Mathematically, trade-offs like these are often explored through multi-objective optimization. Engineers define objective functions subject to constraints and identify solutions along a Pareto frontier. Along this frontier, improving one parameter necessarily worsens another. For example, minimizing weight while maximizing strength yields a curve of feasible solutions rather than a single answer. Selecting a point on that curve requires contextual judgment, informed by safety requirements, budget limits, and life cycle considerations. Engineering decisions therefore incorporate both calculation and prioritization. Cross-industry comparison reveals that this balancing act is universal. In medical device design, increasing stiffness may improve durability but reduce patient comfort. In civil infrastructure, adding redundancy enhances safety but raises construction cost and project timelines. In software architecture, stronger encryption improves security but may reduce processing speed and user convenience. Across disciplines, optimization is constrained by interacting variables that resist simultaneous maximization. Modern systems engineering formalizes this complexity. Requirements are decomposed, trade studies compare architectures, and lifecycle models evaluate long-term implications. Simulation tools allow engineers to explore parameter interactions before physical prototypes are built. These practices do not eliminate compromise, they make compromise explicit and measurable. Transparent evaluation reduces the likelihood that hidden trade-offs will emerge unexpectedly after deployment. Trade-offs also explain why engineering solutions evolve over time. Advances in materials, computation, or manufacturing shift constraint boundaries. A new alloy may allow higher temperatures. Improved battery chemistry may reduce mass. These developments expand the feasible region of design space. However, even as possibilities expand, trade-offs remain. Each innovation reshapes rather than removes competing objectives. Modern engineering systems are not designed to be perfect. They are designed to be balanced. Every system reflects a series of deliberate trade-offs between performance, reliability, cost, safety, efficiency, and robustness. These trade-offs are guided by physics, data, standards, and human needs. When a system seems overbuilt, underpowered, or inefficient, it is often because engineers prioritized a different objective, one you may not immediately see. Understanding trade-offs reveals the hidden logic behind engineering decisions. It explains why systems fail the way they do and why they usually fail safely rather than catastrophically. Trade-offs are not compromises in quality. They are the essence of engineering. If you enjoy clear, research-driven explanations of how modern engineering systems really work, consider subscribing to Engineering Manual. New videos explore the logic, constraints, and decisions behind the technology shaping our world.